All right, this one is on gas stoichiometry. So when we did stoichiometry, when we had gases and we wanted to find the volume, we were using 22.4 liters per mole. That number comes from using the ideal gas law and plugging in the STP values for 1 mole. You get 22.4 liters. That still works if you're at STP. So when we do the AL assignment, first 3 or 4 problems, you can use 22.4 liters per mole. That's still allowed. But if you're not at STP, this value no longer applies. What we can do instead is use stoichiometry to find moles, which would be N, and then we can use the ideal gas law. So gas stoichiometry is combining the ideal gas law, PV equals nRT, or PivNert, with dimensional analysis stoichiometry. So we're not going to throw any BCA charts at you. This will just be the ones where you're doing the fractions. So we have 2 examples. First one, you're going to be given grams and you're trying to find volume. The other one, you're starting with volume and you're trying to find grams. So I gave you these 2 because they're the 2 ways that it can be solved. So let's look at our first problem. In this one, we have the 3.535 grams of sodium bicarbonate. So in this one, we're given grams of a non-gas. So sodium bicarbonate, that's the solid over here. In that case, step 1 is stoichiometry. We're going to use that to find moles. Just N. And then we're going to do the ideal gas law. So this will be 2 steps. First step is the stoichiometry. So in order to plug in the values into PV equals nRT, we need a gas. So this one specifically is asking what volume of carbon dioxide. So we're trying to find CO2. So our stoichiometry is going to switch from grams of sodium bicarbonate to moles of CO2. So we'll start with our 3.535 grams of NaHCO3. Divide it by the molar mass. So that would be 84.007 grams for sodium bicarbonate. And then we can switch to carbon dioxide. So this reaction, kind of hard to tell just looking at it, but it is balanced. So that would be 1 mole of sodium bicarbonate for 1 mole of CO2. And when we do that, we're going to keep 4 sig figs. So I got 0.04208 moles of CO2. And we're not going to switch this to grams because at the end, we want volume. So if we switched it to grams, we'd have to divide by the molar mass anyway. So you always stop at moles. And this number, this is going to become our N in the ideal gas law. So we're done the stoich part. We solve it for moles of the gas. And then in part 2, we're going to use the ideal gas law to solve for volume. So in the problem, you're going to be given pressure and temperature. So our temperature is 45 degrees Celsius, and our pressure is in atmospheres. So with this one, we're going to need an R value that uses atmospheres. I'm going to use the one that has liters. It will be a small volume in liters. Milliliters is fine too. But first, temperature, as always, should be in Kelvin. So 45 degrees Celsius is 318 Kelvin. All right, so plugging in our numbers. So pressure given in the problem, so it is P. So that's going to be 622 atm times volume, that's the one we don't know, equals N, that's what we just found from our stoichiometry, times R. So you can use either the R that gets you liters or milliliters. I'm going to do the liters one, but it has to have the atmospheres. So that one, if you look at your chart, is going to be the 0.08206 liter atmospheres mole Kelvin. You could also use the 62.06 milliliter atmosphere mole Kelvin one. And then our temperature is the 318. So then we're trying to find volume by itself. Divide by 2.622 on both sides. Plug all of that into your calculator. Now with this one, the one that's going to limit our sig figs is the temperature that only has 3. So our final answer is going to have 3 sig figs. So for volume, I got 0.418 liters. And if you had solved that in milliliters, that would be 418 milliliters. It doesn't specify which volume, so you can use either one. So that's it. So we had mass given in the problem, which told us we were going to do stoichiometry first and then the ideal gas law. The other way you can do it is if you're given pressure, temperature, and volume in the problem, you're going to do the reverse. We'll do ideal gas law first and then stoichiometry. So that's what we're going to do for the second one. Let's see if I can scroll here. There we go. All right, so for number 2, we've got, this is our volume, temperature. Let's switch that to Kelvin. That's going to be 1498. And then pressure. So in this one, if you're given volume, then we do ideal gas law first. We're going to solve it for moles. And then we do the stoich. Okay, so for this one, we know pressure, temperature, and volume. And this one, we've got kPa and liters. So that tells us that our R value is going to be the 8.314. Based on our chart. Then we have all our information. We're solving for N. So this one in the ideal gas law, I'll just write the equation again. PV equals nRT. Pressure is the 475 kPa. Multiply that by the volume. Moles is what we're looking for, so we don't know N. The R value is based on the kPa and liters. And then temperature is 1498 Kelvin. All right, so I didn't simplify. I'm just going to keep the whole numbers there. All right, so this all gets plugged into your calculator. This one we have to round down to 3 sig figs because our pressure and volume only have 3 sig figs. So I got an N of 0.0907 moles. And notice both of our moles were pretty small, and that's fine. Gases are very spread out. So we would have a small number of moles. Okay, now that we have moles, we want to identify which gas that was for. So back in the original problem, it told us that's for N2O4. And that matters when we do our stoich. So this becomes our starting value for the stoichiometry. We have moles, so we can go right to the part where we switch substances, and then we can find grams of nitrogen dioxide, which is NO2. So this becomes our starting value for the stoich. So in our equation, we've got 1 mole of N2O4 2 moles of NO2. And then we want to multiply that by the molar mass of NO2, which is 46.006 grams. All right, keeping 3 sig figs, I got 6.52. So both of these things are things we know how to do. We know how to do stoic problems that look like this. We know how to use the ideal gas law. Gas stoichiometry is just putting those together. So either you're going to be given volume, temperature, and pressure when you do ideal gas law first and then stoichiometry, or you'll be given grams of something that's not a gas or not the gas you're looking for, and then pressure and temperature. In that case, you do stoichiometry first and then the ideal gas law. So that's how to solve these problems. And that's the end of the video.